Hi everyone, I'm Arsha. I welcome you all on behalf of Astron TKMCE to this talk section about parallel worlds. First of all, I welcome our speaker, Mr. Paulose Thomas, who is here to enlighten us with this knowledge providing speech. Welcome, sir. Now I extend my hearty welcome to everyone gathered here in this meeting. Enjoy the talk and impart a lot of knowledge. Welcome all. Sir, now you may take over and start the section.
Thank you, Arsha. Anyways, good evening, everyone. This is Paulose Thomas, and thanks a lot, Savitri and Arsha, for that welcoming. I'm so happy to see you. Nearly 84 participants are here, and especially the word used by Savitri, that scientific temper. That's exactly what we need nowadays, and that's what we lack. So today's topic is all about parallel worlds. So let me share the screen. Just give me a second. Okay, so the word parallel worlds, I believe all of you have, who are present here, they might have heard about the word parallel universe, and that's maybe why all of you are here. So yeah, parallel universe and parallel world, I selected the word parallel world because of some reason, which is what you are going to soon see about it. Okay, so before directly going to the concept of parallel world, I need to show you like how we can enter into these kind of worlds or different universes. Okay, that's what we need to know first. What are the different ways that you can enter into this parallel world? So here you can see on the screen, okay, we have 4 options basically. Okay, number 1, quantum mechanics, something which most of you might be really are not so what I can say, don't like the topic quantum mechanics, because something which is very difficult. That's what you might have heard about quantum mechanics, right? Second one is M theory or superstring theory. Okay, that is full of higher dimensions and weird stuffs are there. Then third one is inflation theory. You can enter into the parallel universe using that particular theory. And the fourth one is anti-parallel universe with time reversal. What I am preferring here to go to the parallel world through the first option, quantum mechanics. So that is what the right channel is, I believe so. Not because of all other theories are wrong. It's mathematically very elegant, but quantum mechanics has a slightly, what I can say, a higher advantage over the other theories. Let's see what it is. Okay, so let's have a quick roadmap to this world of quantum mechanics. So here you can see a small quote from Richard Feynman that if you think you understand quantum mechanics, then actually you don't. It's actually slightly misunderstanding or misleading statement. Why? Because we do really know quantum mechanics, and that's why we are using mobile phones, the laptops that you are using, understand, or maybe iPads, or maybe latest electronic gadgets. It's working because quantum mechanics is real, understand? So that is not a fictional science. It's really possible. Okay, it's real. So let's get into the quick roadmap to quantum mechanics. So here you can see a list of scientists. Okay, all have their own contribution to the latest modern physics. So starting from René Descartes, who actually predicted light as pressure waves that actually pass through a medium called as plenum. Okay, Isaac Newton, who has brought the concept of what we can say corpuscular theory. Again, Newton's concept about light is basically, it was full of particles, understand? It was Christian Huygens that actually came into the scene and said that, no, light is not always particles, basically waves. And Thomas Young's famous double slit experiment. Its observations, still we are thinking about it, pondering about it, and still it's unknown. So many results of double slit experiment is unknown. We will get into that later. James Clerk Maxwell, who actually combined the concept of electricity and magnetism. He also believed in the medium called ether. Max Planck, who brought the concept of quantum or quantum. That is what we are sticking upon to the entire presentation. Albert Einstein, who proved that light has the particle nature using photoelectric effect. Then Niels Bohr, who actually brought the new concept of atom model. Louis de Broglie, who combined the matter concept and particle concept and wave concept. And you can see Davison and Germer, who actually proved Louis de Broglie's concept by using the diffraction experiment of electrons. Even though all these scientists have their own contribution, these four scientists, what you're seeing on the screen right now, have a great contribution to quantum mechanics. The first one, Irwin Schrodinger, who brought the concept of Schrodinger equation and the thought experiment, which all of you might be knowing, Schrodinger's cat. Then comes Max Born, who actually gave some meaning for Schrodinger equation. Even Schrodinger didn't believe his equation whether it will work or not, but it was Max Born who actually gave them meaning for Schrodinger equation. Then came Werner Heisenberg, who brought the concept of uncertainty principle and matrix mechanics. And finally, Hugh Everett, who took the concept of quantum mechanics to parallel worlds. Okay, so that is what we need to know, parallel worlds. So before going to parallel worlds, we need to know something about quantum mechanics. And to know quantum mechanics properly, okay, let's discuss very two famous experiments that you people might be already knowing. The famous double slit experiment. So you might be thinking, why I'm explaining double slit experiment when I'm talking about parallel world. So this is the best experiment I can show to you by and I can correlate what exactly is happening in quantum mechanics. Okay, so all these things you might be knowing, you have studied in 12th grade in chapter wave optics. So let me tell you very quickly that you keep a light source, okay, and then you keep two slits. The light source should be monochromatic, and you keep a screen. Fine, the light will pass through that two slits and you get a pattern, which is a wave pattern, or we call as interference pattern, which means basically there will be a central bright band followed by alternate bright and dark bands. If you see some pattern like that, it's a clear evidence for wave nature, which means we can conclude that light is basically wave. Okay. Now, if you replace the source of light with a box of sand or a bucket of sand, what do you see? You can see basically particle pattern, because you won't get an interference pattern here. Why? Because sand will fall through those two slits. It will pile up as two bands, and that's what we call as particle or particle band. Yeah. The other one, we got a wave pattern. Now we are getting a particle pattern. Fine. Let's do the same experiment with an electron gun. And this is where slowly that weirdness will start. Okay, so pay a close attention. What we are doing is we are taking an electron gun which can shoot electrons one at a time. Okay, now out of those two both slits, we are covering one slit. Okay, and the electrons will flow through the only one single slit. Fine, the pattern that you are observing is very predictable. There is nothing much confusion in that, but the next slide that you are going to see will really make your heads scratch. And that is when you open the second slit. When you open the second slit, you are getting a wave pattern or interference pattern. That means if an interference pattern is shown by something, let it be anything, it should be of wave nature. Got it? So from this, we can say that electrons are basically waves. That's why you are seeing interference pattern. But the click is like, this gun is only shooting electrons one at a time, and still it is showing what? Interference pattern. What does that mean? It means there is only one conclusion. It means an electron, once it is out from the gun, it is choosing both the slits at the same time. Okay, it's choosing both the slits at the same time. Then only it can superimpose, okay, after the slits. It can superimpose after the slits and give you a clear-cut interference pattern or a wave pattern. So that's the only option. Fine. Okay, we are ready to believe that electrons are waves. Fine, it's not a big issue. What's the big deal in it? You might be thinking. But it will become more crazy when you try actually to observe like how that electron is choosing that slit. Which means imagine you are keeping a detector nearby any of these two slits. Let it be slit A or let it be slit B. Something like this. Immediately what you see is not a wave pattern at all. It's a particle pattern. You didn't do anything else. You just kept an observing device, a detector near to one of the slits. You keep it anywhere, not an issue. But if it is detecting the electron, okay, if it is observing the electron, that entire wave pattern will collapse and it will show you a particle pattern. So there comes the question. How come electrons know that we are observing or something is observing it? And how come its entire wave nature gets collapsed suddenly to a particle pattern? So is electrons are having consciousness? No, never, because that doesn't make sense. But then how come electrons know that something is observing it? So we'll do one thing. We can go around the room and turn off that detector, and let's see what will happen. If you turn off the detector without knowing, or without even the electrons know that we are even moving, or let's make a call to the other side of the room and let's say to our friend to turn off the detector, and let's see what will happen. If the detector is turned off even without knowing or making the electrons know, you will get once again a wave pattern. Weird enough, right? So this is what we call as the measurement problem. The measurement problem means that sudden collapsing of wave nature to particle nature. The moment you observe it, that's it, done, finished. You will get a particle pattern. So how this is happening, it's still unknown. That's the reality. It's still unknown that how wave pattern, okay, it's getting collapsed to particle pattern. That is one experiment that you should know regarding to the before the entry to quantum mechanics. Why? Because here what's happening is that electrons are superimposing or it's undergoing superposition or superimposition, and you are getting that wave pattern. But you keep an observing device, you are getting a particle pattern or particle band, and keep that in mind. Let's see what will happen in the next experiment. Once again, this also is very familiar for all of you, because all of you have studied the 12th grade physics and have come here. So there comes the concept of polarization. In very simple terms, I can show you a picture here. Right here you can see a picture where the unpolarized light. It's slightly technical term. Just understand that light is vibrating in all these different planes. Okay, in different planes it's vibrating. Just imagine that a light wave is vibrating like this. Okay, it's vibrating in all the planes. It's passing through a polarizer. Fine. And what you get is a polarized light. That's how we have studied. Okay, wait a second. Now this polarized light is entering to another polarizer. We call it sometimes analyzer, but forget about that word. A second polarizer. Let's name it as second polarizer. The light that comes out of the second polarizer, okay, definitely light will be coming, and its intensity will be reduced depending upon how the polarizer and analyzer are kept. Understand? So if a polarizer is there and analyzer is there, if they both are parallel, the entire light will come through the analyzer. If they both are perpendicular, not a single light will come through the analyzer. But if they are at some other angle, you will get light. This is something we have studied. Then you might be thinking like, what is weird in it? This is something that we have already studied. The observations we know, results we know. What's the problem here? The problem is my question, what I'm going to ask. How come the polarized light that was vibrating in one single plane? It was vibrating in one single plane because it came out from the first polarizer. How come this polarized light come through the second polarizer at all? Because the second polarizer is at a different angle. Okay, so actually imagine this is the second polarizer. Okay, my hand is the second polarizer. So this is how the light is coming, right? If at all it is coming, if at all it is coming. But if in case my second polarizer is tilted by an angle, by 30 degrees, 60 degree, anything, the light which is coming from the first polarizer should not even go through that, right? The light should actually tilt an angle in order to go through this. So which means the concept that we studied, that means the light which comes from the first polarizer is plane polarized, has to be changed. Understand? And that is where, you know, these spooky things will start. Because light, when you actually keep a polarizer, you are doing a measurement, fine. At that particular moment, we can say that light is plane polarized. But once it is out from the polarizer, it's again in superposition. It's again in superposition. That doesn't mean that light is, you know, in a superposition state of all the angles, but light will be in a superposition of most of the angles, and that is why it is coming through the second polarizer. So the concept that we studied, that the polarized light is coming through the first polarizer, doesn't mean that it is sticking onto one single plane. It's actually in a superimposed state. Why? Because the one which we have taken, light, is a quantum particle. Understand? So we should know what exactly a quantum particle is. Then only we can unfold the mystery of these things, or these two experiments. Let's see what it is. But before that, just see this experiment. You can see two polarizer. If they both are at 90 degrees, you won't get any light. Okay, simple experiment. And when light goes through the first polarizer, it will, and when it is passed through the second polarizer, if it is at 90 degrees, there is no light. If it is at any other angle, some amount of light will be coming to it. My question was, don't forget that question, how come the light which was vibrating in one single plane even passed through the second polarizer? The answer is superposition of light. Okay, now let's get into the basics, you know, basic things that you should know about quantum mechanics, because without knowing these concepts, we cannot explain or we cannot enter into the parallel world. That's why. So a very simple definition that we can give that in physics is a quantum, or a quanta, which is the plural, okay, is the minimum amount of any physical entity. You can consider like an electron as a quantum particle, or you can consider a photon as a quantum particle, because it is the smallest of its type. You cannot even subdivide those things. That's why we call it as a quantum particle. Now these quantum particles, okay, these quantum particles like electron, photon, and all those things have a special characteristics things. I mean, they entirely behave in a different way. So that is what we are going to see. So the next slide, what you see, might, you know, slightly disturb you, because equations, we never like equations, we know that, but still only two equations, just for, you know, namesake purpose. Just understand that this is this thing, and you don't have to go deep into it and should know what it is, but you can refer it later. So as simple as that, I can say it that quantum particles, okay, like electron or a photon, here you can see they can be mathematically represented as a wave function. Just remember this word, wave function, we need it later. Okay, just see that how beautiful it is. You can see a spear, like a fork, and so many things. Great, fine, let it be like that. That's a wave function mathematically, which can be represented as graphically like this. Here you can see a real, and it's written real and imaginary. That means a quantum particle, or okay, a quantum particle can be represented as a mathematical function, as, and we can call it as a wave function. Agreed? That is the first one. The second one is the graphical representation of that wave function. Okay, that much you understood, right? Now this wave function, you square it, you will get a pattern like what you see on the right side. Okay, a pattern like this. You can see a inverted V curve, and that is what we call as probability distribution function, or probabilistic function. Just understand the words only. Okay, I'm not going deep into that. Just for understanding quantum mechanics, I'm telling these words. Now there is one more thing that you can see at the bottom, which is basically the Schrodinger wave equation. Schrodinger wave equation, something that you can compare with Newton's laws of motion or Newton's equations of classical mechanics, because in classical mechanics, you can see here, Newton's laws of motion will give you, or it can predict the position, it can predict the momentum, or literally it can predict where it is if you know the initial conditions. Fine. Literally it can predict where the particle is in the future if you know initial conditions. The same thing can be done by Schrodinger equation. Understand? So Schrodinger equation will give you the information, the quantities about a quantum particle. Okay, it can measure some quantities of a quantum particle in over a time. Understand? Over a time, it can predict where the quantum particle is. Just for that purpose, we use Schrodinger equation. But to understand the Schrodinger equation, that was actually, even though Irwin Schrodinger has given this equation, it was Max Born who actually gave some sense to it. What he said is that by reading the Schrodinger equation, it will be really complicated. Why? Because it's a combination of real numbers and complex numbers. We never see complex things in real life, correct? So this kind of probabilistic function, I mean that inverted V-shaped curve is what the reality may be. Understand? Now, these quantum particles, they have some properties like, say, superposition, uncertainty, entanglement, decoherence, quantization, and quantum tunneling. All these things are so crazy, what crazy words I can say, in which superposition I already shown by 2 examples using dual nature and polarization. Don't forget those 2 experiments. Now, let's see what uncertainty is. Okay, let's see what uncertainty is. It's actually very easy. Again, something that you know. But let me clearly show you how exactly it works. Here you can see several plane waves, okay? Several plane waves. And when you club all together, we can use the word superimpose. When you superimpose all these waves, you are getting a wave function or a wave packet. So remember, wave function, we mathematically already wrote here and graphically already represented below. But that graphical representation includes real and imaginary numbers. And here I'm only including real numbers, otherwise it will be very complicated. So you are getting a wave function. Now, what's the problem of this wave function is? You can look into that and you can only say that its wavelength is not certain. Understand? Its wavelength is uncertain. But you take one single plane wave from that, you can easily calculate wavelength. Understand? So wavelength should be known in order to calculate what? Momentum. Understand? So this particular wave packet or wave function will not give you any information about what? I mean, it will give information, but it won't give an accurate information regarding momentum. But it can give the information about the position, because you can see that wherever that high peaks are there, there is more chance for finding the quantum particle. So that is why you can see here the below graph. Okay, towards the left, here you can see where the electron or photon you can find with more probability or high probability. Understand? Where on the other side, okay, where on the other side you can see, if you take a plane wave, you can easily calculate the wavelength. You will get a clear-cut idea about momentum, but you can't get information about position. So on one side you are getting what? Information about position, but not about momentum. And on the other side, you are getting information about momentum, but not position, which is what basically uncertainty principle is. You cannot simultaneously calculate the position and momentum of a quantum particle. So many people actually misunderstand this concept that you can never measure anything accurately. That's not what Heisenberg meant. What he meant is that you cannot simultaneously calculate these 2 things together at the same time. Okay, fine. That's about uncertainty principle. Now, here you can see that basic wave function, and you take that wave function, you square it, you will get the probability distribution, inverted V-shape. Okay, don't forget that inverted V-shape curve. And there you can see the high probability of finding an electron. And here you can see this point. You can see where my cursor is. You can see that is the lowest probability. You can't even find an electron or a photon there. Understand? So wherever you can see peaks, you can see where there is a high chance for finding a quantum particle, or wherever you see flat curves, you won't find that quantum particle at all. Clear? Now let's get into the measurement problem. Here you can see that inverted V-shaped curve. Okay, these graphs are actually, actually been simulated using the original Schrodinger equation itself. And here you can see a high peak, and that happens while during measurement. So on one side, it's all about the quantum world. Okay, and that is what you can see here, an inverted V-shaped curve where you can find quantum particle anywhere in that region. The moment you make an observation, you will get a peak. How? No idea. Understand? How? We don't know, but that's how quantum mechanics is. So in the quantum world, they are happily living like waves. The moment you make an observation, it will collapse. Understand? It will collapse into particle nature and will show exact position. So that is what we call as the measurement problem. So I hope few terms you already understood by this time. So let's get into the famous example of, or famous experiment of, or famous saying of seeing two things at a same time, or at one place. All these things we can see here. So here you can see a wave function, once again a wave function. So different types of wave functions you can draw. The only thing is that those wave functions should obey Schrodinger equation. Understand? Simply you cannot draw any graph. Okay, the graph, if you are drawing a graph and if that graph is obeying Schrodinger equation, then we can say that that particular graph is of some quantum particle. So this particular graph is being obeyed by Schrodinger equation. So here you can see at the same time you can see very high probability of finding electrons. Understand? And here you can see that flat portion. You can see that flat portion. You will never find an electron at all. So this is something which we can refer to a Malayalam movie, say Nandanam, in which Jagadish Srikumar, seeing at one time in multiple locations. We can call it as, say, some Kumbidi effect. Let it be like that. So here the wave function, I hope you understood. You can see quantum particles at one particular moment at two different places. Got it? So that's how weird it will behave, which means the question is whether I'm actually presenting this presentation right in front of you. There's a question like that. Let's get into that later. Schrodinger cat. Schrodinger cat is something which, it's a thought experiment, very famous thought experiment. And even though Irwin Schrodinger has actually didn't conduct this experiment, but it's really thought-provoking about this particular experiment. Let's see what it is. Take a box. Okay, keep a cat inside that. Now take a radioactive atom which can decay in 1 hour, where there is a 50% possibility for that, or 50% chance there is no possibility of decaying it. Okay, then this particular radioactive atom, if it decays, it will be detected by a detector. You can see a detector here, and that detector will trigger the hammer. The hammer will come and hit the poisonous glass bottle kept inside the box. The cat will die if it detects. If it does not detect, what will happen? The cat will be alive. So let's say if it detects, as I said, the hammer will be triggered by the detector. It will break the glass bottle, cyanide gas, the cat will die. And if it not, the cat will be alive. Agreed? So the point is, until and unless you open the box and see what actually has happened to the cat, it's in a superimposed state, something which we can't believe with our proper thinking, because how can be cat dead and alive at the same time? Fine, the radioactive atom is there, it's a quantum particle, it's in a superimposed state. We cannot say, because that we already proved using Schrodinger equation. We showed wave functions mathematically, we already proved it. Dual nature is showing that, polarization is showing that, superposition is real. That is real. Or you simply throw two stones into water, you can see what waves superimposing together. Superposition, that is there. But here, that is not the case. Here, the radioactive atom is, since it is in a superimposed state, that all the other things inside the box, you have to say it is in a superimposed state until an observation is done. The moment you make an observation, the cat will be either dead or it will be alive. The cat will be either dead or it will be alive. That means that entire wave function collapsed to particle nature. Understand? So there was a 50-50% probability, but immediately the moment you make an observation, either the cat will be dead or the cat will be alive. That is the problem. How will we solve this out? Because with a normal thinking way, we won't get this. This is not how science should work, right? Superimposition and all these things, and that for real things, whether it actually happens. So that is where interpretations come. How you should interpret this particular experiment. There are many interpretations. None of them are actually proved. But the most famous three interpretations is Copenhagen interpretation, many worlds interpretation, which is basically the parallel world concept, and the cosmological interpretation. First, I will say Copenhagen, then I will say cosmological, and then I will get into many worlds or parallel worlds. Copenhagen interpretation, actually put forward by Niels Bohr and Werner Heisenberg, they told that, okay, fine, the wave function is not physical because it's mathematical. It's strictly mathematical. You will never find a wave function. You always see the particle pattern when you make the observation. So forget about wave function. That's what Niels Bohr and Werner Heisenberg said. And what they believed is that the reality is basically the observation. Understand? It's not otherwise. The reality will only come during observation. So the interpretation has a tagline has come to that particular interpretation, which is also called as shut up and calculate interpretation. So what it meant is that don't go so much behind the wave. Anyways, you are getting a result, stick up onto that and do the calculations. But we know that that is not how science accepts something. Science will always dig deeper and deeper until it reveals everything. Correct? So not a single physics concept actually describes how the wave function is collapsing to particle pattern, but Copenhagen interpretation is actually very well satisfied with the observational results. They are not going behind the wave function. Fine. So that is the first interpretation. The second one is the cosmological interpretation, which is actually an extension of parallel world interpretation. But since we have to focus more on parallel world, let us skip for the last. And here, cosmological interpretation says that it's really interesting. It says that there are infinite universes. When I say the word infinite, you all might be thinking, what, really? Infinite? Is there something like that? Infinity? Okay, fine. But imagine there are infinite universes. Okay, and you are doing experiments in one particular universe. Fine. And you are getting a result. Fine. At the same time, in some other universe, you are getting the alternate result. Understand? Which means, for example, I can show you by a simple example here. Imagine there is a chance of finding an electron. I mean, 30% chance of finding an electron over here and 70% chance of finding an electron over here. According to cosmological interpretations, it says that out of these infinite universes, 30% of the universes, in 30% of universes, you will get the electron right here itself, and the remaining 70% of universes, you will get the electron over here, which means the probability is maintained. That is the advantage of cosmological interpretation, because it maintains the probability. It's not destroying the concept of probability with real world. Understand? But that is not how parallel world takes it, because parallel world interpretation is something different, or many world interpretation is something different. It's actually proposed by, as I already said, 1957 by Hugh Everett. It's not just one single person, it's actually a collection of scientists. Actually, he put forward the concept, but later on all the scientists took forward that concept, and they believe that Okay, Schrodinger equation, they are ready to take it. Okay, they are ready to accept the Schrodinger equation, but there is no collapsing of wave function happening. What you actually see when you see a particle pattern is just one single result, out of many other results. That means, for example, if you take the Schrodinger cat experiment, when you take the Schrodinger cat experiment, the moment you open the box, you are seeing the cat dead or alive. Imagine in our universe, I am seeing the cat dead. At the same time, the universe, just before opening the box, the universe branched out or splitted, and in the other universe, the cat is alive. So if I'm seeing here as dead, in the parallel universe, it is seen alive, which means the entire universe is not getting duplicated. Don't just think like that, but it's subdividing or branching out into two. Understand? This is where the parallel world interpretation says that then there is no meaning of probability, because in both universes you are saying, or there is 100% chance of getting the result. Here 100% dead, here 100% alive, or the other universe you are saying the cat is 100% alive. So then comes the question, what is then probability is, right? So parallel world interpretation, that's how you have to interpret it. For example, to understand it more, you should know another property of quantum particles, which is entanglement. Let's see what entanglement is, and then let's go back to a Schrodinger cat experiment, and let's connect these two to understand how actually the interpretation means. Imagine two electrons. Here you can see these two electrons are ideally different, and they have got separate wave functions. Red, blue, two separate wave functions. Fine. Now, the moment it interacts, the word is entangled. Okay, the moment it interacts, they get entangled. Once it gets entangled, then they both have one single wave function. Got it? So the moment it gets entangled, it's having the same wave function. Remember the wave function graph, the wave function sphere, and the spoon or fork, what that equation, all those things. Okay, so here they are getting entangled. Now take these two electrons to faraway distance. Okay, take these two electrons to faraway distance. Let it be millions of light years away, not a problem. And you make an observation in one of that electron. Immediately you will get the result of the other electron too. For example, if you are calculating the momentum of or position of one particular electron, you will get the momentum of the other electron, because momentum has to be conserved. Understand? So at one particular point, if you're making an observation of one particular electron, instantaneously at that right moment, you will get the information about the other electron on the other side. There comes the question then, did something actually communicated faster than light? That's the question. So the best way to understand is that while entangling, okay, while they are interfering, we can say that they both had one single wave function. That's how the latest physics take it. Understand? So while it got interfered, or while it got entangled, that two particles got the same wave function. That is what I'm going to extend it to Schrodinger cat. Let's see how it works there. In Schrodinger cat, okay, remember the climax. The superposition was there, right? And everything was in a superimposed state, which means it's also entangled. Understand? Radioactive atom, here you can see it's already in a superimposed state. It can there is 50% of chance for getting decayed, 50% chance not getting decayed in next hour. Then I can say that this particular quantum particles gets entangled with all the air molecules, with all the stuffs inside that box. And the wave function of all these quantum particles is one single gigantic wave function. Understand? It's one single gigantic wave function, including the person who is observing it. Understand? The moment you open the box, it gets splitted, or the word is decoherence. So remember that list of properties of quantum mechanics. It will decohere into two, and one of your version of the other universe see the cat dead, and here we see cat alive. Understand? So don't think that they both are same. They actually were same, but now they both are splitted into two parallel universes, and now you both are two different copies, and he will be having his own happy life, and here we'll be having our own happy life. Understand? But remember, energy is still conserved, and that's exactly what Schrodinger equation says. The entire equation is basically energy conservation equation. So don't think that energy is not getting conserved here. Energy is strictly super duper conserved. Got it? So that's how it splits into two. That's how the parallel world interpretation is all about. There are many other interpretations, like you can see on the list, like quantum Darwinism, transactional interpretation, so many blah blah stuffs you can see here. And that in all these ways you can what explain the concepts of parallel world, in which we strictly focused on the parallel world interpretation. And through parallel world interpretation we understood how you can explain Schrodinger cat or dual nature experiment or polarization experiment. Understand? And there are a few implications. I'm not using the word application, but instead I'm using the word implications of these, all these things what we came to know. The very first one is that the grandfather paradox, something which you all are, maybe waiting for, which is time traveling, right? You are born and you create a time machine, you go to past, you kill your grandfather before he meets your grandmother, and then what will happen? Father is not born, you are not born, you didn't create the time machine, you didn't go to past, means you didn't kill your grandfather, he's alive, means your father is born, you are born, and it's a paradox now, it's getting looped. So actually what will happen when you go to past and when you kill your grandfather before he meets your grandmother? It's a very big question, right? That's these kind of steps are what we call as paradoxes. We have two solutions. One solution is that, okay, you build your time machine, you go to past, agreed, but you are not going to the past of your same universe. The timeline is changed. If the timeline is changed, then from the first universe you are vanished, fine, it will go like that. Now you are present in the second universe, and that too in the past, and you are killing your grandfather, nothing will happen to you because it's an alternate timeline, it's a different universe. There you can live happily and you can live your life, but that is not so a thrilling concept. Why? Because we don't like these kind of endings. We need something very, very thrilling finishing, right? So there we should understand, just let's take what happens if it is one single universe and if there is any solution. There is a solution, and that's exactly what quantum mechanics say. Quantum mechanics say that, okay, fine, you go to past or you kill your grandfather, but according to quantum mechanics, he is dead and alive at the same time. Superposition. Understand? So if he is dead, then you are there. You can be there, or you are not. You have not gone to the past, or you are right there in the present itself. You are also in superposition. So according to quantum mechanics, the grandfather as well as the time traveler, which means if you are traveling, these both people are in a superposed state. Understand? So that's how you can solve the grandfather paradox using quantum mechanics. So you don't need an alternate timeline. You can actually take the same timeline, same universe, and you can fix this issue using superposition. So that's actually possible. So that is regarding time travel. Now something regarding higher intelligence. So suddenly from where this higher intelligence comes, if you ask me, you can see this picture, and you might have seen a movie called as 2001: A Space Odyssey, where you can see a giant monolith, suddenly appearing in front of a lot of apes. And this actually gives the significance that we people may be living, people may be living with higher intelligent beings where we are not able to understand what it is. Maybe it might be a millimeter away from you. Okay, it might be a millimeter away from you, and they might be controlling everything, but we don't understand because they are in higher dimensions maybe, or they are extremely highly intelligent for us not to understand. Our brains are not able to perceive all these things. Understand? So that is one thing that you can connect with multiple universes. Maybe these higher intelligence may be coming from other universes, understand, and they might be our universe might have joined together, and all these things can come to our universe, and it goes like that. You can make the story the way you like. And when you connect this quantum mechanics to reality, few things that we can see here, maybe in a parallel universe, this corona, COVID, all these things might not be there itself. Maybe in some other parallel universe, our Chandrayaan-2 might have successfully landed on moon. Maybe in some other parallel universe, India might be the most developed nation. Maybe in some other parallel universe, you can see Subhash Chandra Bose might have died peacefully, understand? And maybe in this universe, your love might have rejected. Maybe in some other parallel verse, your love might have got accepted. Now you might have understood why I put the blocks in the different sizes, because probability. Understand? So it depends upon the probability. So the higher probability, the higher size. Fine. So what all you saw till now, maybe the entire webinar, okay, you have watched now might be in a universe with reversal of time, or in a mirror universe, since they both are practically difficult to prove your consciousness. Okay, I have presented the entire slides what you watched absolutely in the reverse order. Yes, even without giving a chance for your brain to solve out this paradox also. The first slide you actually saw is actually the last one of the presentation, and the last slide you saw is the first slide of the presentation. So let me all welcome you to Parallel Worlds. Thank you.
Thank you so much, sir, for this informative and amazing session. The session was indeed thought-provoking. And I think and I believe that many of you present here will be having some queries or doubts. So it's your time. You can ask right now.
Good evening, sir.
Good evening.
Yes, sir. Thank you for the wonderful session. I have a question. Can you explain that inverted wave function once again? I couldn't get it.
Yeah. So here you can see the mathematical representation of wave function. Okay. That wave function, what we are doing to get that probability distribution curve is directly we are squaring it and we are plotting it. Understand? Wave function we are taking and you are squaring it and you are plotting it. That's what you are getting, that only positive values. That's why you are getting that positive values, the probability distribution. Understand? So what you do is basically you need to take that function, you square it, you plot it. Schrodinger equation gives you the information about that quantum particle over time. Is that clear now? It's the same representation of the Newton's equation in classical mechanics.
Thank you, sir.
So we have few questions in the chat box. Ajay is asking, sir, I have heard that in grandfather paradox, killing our grandfather as well as not killing him happens simultaneously. How?
Killing our grandfather as well as not killing him happens simultaneously. Exactly. That's what the concept of quantum mechanics is also saying. You are killing at the same time you are not killing, or you are observing the cat is dead at the same time you are not observing the cat is alive. The problem is the moment, we can take it like this, you can take it as a fictional story. The moment your brain actually decides to kill it, there itself the quantum particles, okay, it's decohering, it's actually splitting into two. And in one universe, okay, fine, in one universe you can say that the person who is actually ready to kill it is going to his own way and killing the grandfather. On the other side, he's not killing. So that is how you can only predict or only interpret this thing. There is no other way to solve this mechanism out. Understand? So the moment the quantum particles the superimposed quantum particles are getting entangled with other quantum particles, splitting occurs, and from there itself two versions of you are forming.
Thank you, sir. We have another question. Can you say your analysis on time travel in Avengers Endgame and Mobius strip model? Also, opinion of time travel by Bruce Banner.
My goodness. For that, I have to watch the movie again. Anyways, yeah, I have watched the movie, definitely, in which this is something that you can say regarding cosmological interpretation. Many universes are there, and it's all about bringing the for example, here I am dead, in the other universe I am alive. Okay, it's all about bringing that me to this universe. Understand? So that is where you can create your loops of our shortcuts in space, and you can bring the personalities of the other universe. You need to go there, you need to convince them, okay, fine, here all are dead, you please come and help us. You can go there through wormholes, and you can invite them. They are all coming to your universe, and yeah, the earth is saved. That way you can solve the issue. But in many of the movies, you can see the time plot is sticking on with one single universe itself. That is where the confusion begins. But if there might be so many problems if you take the same timeline itself, but somehow they will try to bring it all together at one single point. For example, the movie Tenet itself, it begins from one scene, the movie ends at the same plot. Actually, the starting point and the ending point, they both are occurring at the same instant. Understand? So my suggestion or my solution or my analysis for that Avengers movie is this only: go to another universe, invite them to our universe through wormholes. Yeah.
Okay, sir. So another question: can black holes be connecting parallel universes?
Yeah, most probably. Depends upon the size of the black hole. If it is extremely large enough, fine, the black holes may be a connecting path, because if you jump into black hole, you might end up into the opening of a white hole, or you might not, because the way we have understood black hole is there is extremely high I'm not using the word infinite, but extremely high finite density at the center, but we don't know what's actually happening inside the black hole. Maybe there might be a connecting portal. Understand? Especially in the case of spinning black holes, because spinning black holes can actually create a ringularity instead of singularity, and that ring, understand, that ring might be enough to pass through and enter into another universe. Yeah, it might be an opening path.
Okay, sir. So another question: what is the probability of paradox crossovers, say grandfather paradox and bootstrap paradox?
Probability, that's what I said. Probability, according to two different interpretations. In one interpretation, probability is getting destroyed. In other, what I can say, interpretation, there is a 50-50% of probability of killing the grandfather and not killing the grandfather, because there is only two options. Understand? So that is how, since we are focusing on parallel worlds, there is 100% probability of killing the grandfather. At the same time, there is 100% not killing the grandfather in an alternate universe. The problem is, when you connect the probability to reality, which interpretation you are taking, accordingly we have to move, or we have to proceed. Yeah.
Okay, sir. Why come we couldn't calculate the momentum and position of a quantum particle simultaneously?
That's exactly what I showed here. You can see in the screen right now itself. We can see in this particular slide, you can see multiple waves are getting superimposed. Okay, they are getting superimposed to one single wave function. It lost the wavelength concept itself, right? Because if you take one single wave of these multiple plane waves, then there makes sense that you can actually calculate the wavelength. But once it is superimposed, the wavelength nature is gone. Gone means it's there inside, like a hidden variable, you can say, but it's not exposed to reality. So if you take the measurement, you will only get the information about the position, not the wavelength. If not wavelength, you won't get momentum, because lambda equal to h by p, de Broglie equation. So if you take one single plane wave from that, okay, if you are taking one single plane wave, You can calculate wavelength, but position, it's uncertain. You can see the electron can be anywhere at where the peak is high. So there we get the information about momentum, which is lambda equal to h by p. You know lambda, you can calculate momentum, but not the position. Yeah.
Okay, sir. Sir, can you explain why Doctor Strange comes again and again to bargain with Dormammu?
Who knows? We have to go and ask to him itself. Yeah. Next question, please.
Is there Halo Earth possible? Reference Godzilla vs. Kong.
I think I'll become a director soon. Yeah. I don't know about that movie, so I'm not good to, not the special person to say the answer for that question.
Okay, sir. Can a particle exist without mass? If so, will a flashlight start losing weight considering a light also acts as a particle?
Yeah, technically, yes. The answer is yes itself. For example, two ways you can take it. If you take photon, let's say photon has no rest mass, but it has relative mass. That's exactly why, black hole is taking the light into it. Now, another way is that photons can definitely create force. It can create pressure. Imagine you have a torchlight. Okay, imagine you have a torchlight, and what you need to do is that you go to space, you turn it on. In atomic scale, in space, you are actually moving backward, which means something is changing, right? In atomic scale, you are moving backwards, means when light comes out from the photon, okay, because of the force exerted, you are moving backwards. The same Newton's third law, understand, which means mass is getting reduced. Yes.
Okay, sir. Sir, is a positron and electron moving back in time?
It's a positron and electron.
Yeah,
According to time crystals, which is another state of matter, we have really seen that, in extremely subatomic scale, quantum particles can literally go back to time, and that happens in that quantum world only. So that is why I showed you in the very first means second last. According to me, here you can see the anti-parallel universe with time reversal, if you can see on the screen. Understand? So here, that is happening. That is one way of explaining another parallel universe. Understand? The moment Big Bang starts, the Big Bang, when you might be thinking it's a sudden explosion, it's not about explosion, it's inflation. Okay, so sudden inflation occurs. You are getting a universe with forward time. In the other universe, you are getting the backward time. That is another, mathematical explanation for all these things. So for your question, in quantum scale, time reversal is happening. Example, time crystal. You can refer that time crystal. You can literally see something which is in perpetual motion in atomic scale. You can see a small. If in atomic scale, you can see in YouTube, you can see all these time crystals literally moving forward and then going backward and forward and backward, even without any external force. Yeah.
Okay, sir. So how do we know that if it is us having time or time having us?
Space itself is time, time itself is space. The problem is we are not able to perceive it, and that's the problem. We are actually stuck into a three-dimensional world. Understand? We are only seeing two-dimensional things. We are not actually even seeing three-dimensional things. What we can see is a two-dimensional things, and the brain is giving you the idea that the object what you're seeing is a three-dimensional object, and that's it. You can't go further. Understand? Means, according to string theory, M theory, superstring theory, anything, there are higher dimensions up to 11 dimensions, and time is the fourth dimension. So the space and time are interconnected the same way energy and mass is, the same way electricity and magnetism is, the same way, as I already said, space and time is. Understand? So we will never be able to understand that how exactly how to define time or even to feel the time. It's very difficult. What you can say is only that, yeah, we are living in a present moment. Understand? And This present, past, and future are actually, according to physics, are all happening at one single instant, according to relativity too. Yeah.
Okay, sir. So, are the planets expanding and will it explode?
Not as far as now, because the universe expansion is accelerating, and if this is continuously accelerating at one after, say, Google years, or say Google years, we can say that everything keeps expanding, and the gravitation will definitely, it will lose the entire meaning itself, and because dark energy will overrule and everything gets expanded, even planets and maybe even atoms, and it will get ripped apart. We call it as the great rip, but we don't know what will happen. We have to wait and see.
Okay, sir. Could you explain why only one out of all the waves that constituted the wave function was chose to calculate the momentum? What is the physical meaning or analog of a single wave of the wave function?
The second question, what is the physical meaning or analog of a single wave of the wave function? Yes, it's purely mathematical. That's how we should understand this. One second, first question was, could you explain why only one out of all the waves that constituted the wave function was choose to calculate the momentum? Oh yeah, fine, okay. So the thing is, let's go back to that particular slide. Give me a second. So here we are taking one single wave. Fine. The question was why we are taking that one single wave. The problem is we can't take the wavelength of the superimposed wave. That is a problem. You separately take each wave, no problem. You get separate wavelengths. So what does that infer? It means that you are getting different wavelengths. So for the same wave function, there can be multiple wavelengths. I just gave you an example only. Understand? So there is a clear problem with, we can say there's a clear uncertainty in momentum because the wavelengths are different. Why wavelengths are different? Because the stuff that we have taken is actually a superposed or superposition of multiple waves. Understand? You cannot exactly take one wave of it. Understand? So if you take one particular wave, understand, if you take one particular wave, it gives you the information about momentum, and momentum is a vector quantity. You can calculate the momentum of all the different waves, apply superposition, parallelogram law, all these things. You can calculate the resultant momentum, and it goes like that. But about the position, the same way, the superimposed wave you take, and the higher probability or the higher trough or higher crust will give you the probability of finding the electron the most, and the lower places you can find the electron the least. So momentum, it's not by taking one single wave. Actually, we have to do it for all the waves, and then we have to calculate the resultant. Yep.
Okay, sir. So can you please say a few words about Tesseract in Interstellar movie?
Interstellar, yeah, fine. Tesseract is basically the fourth dimensional cube, I can say. It's not cube, and if you ever try to think about Tesseract, that is not Tesseract. That is the reality. Why? Because we can never ever understand the concept of the next dimension. The thing is, because we don't have even an example. Even the pictorial representation what you see in Google is not Tesseract. That's the problem. So we know that if you take a single dot you put, that is 0 dimension. You extend the single dot like this in a particular direction, that is 1 dimension. Now that single line you extend to the next direction, it is a 2 dimension. Now extend that plane into the third direction, it becomes a cube. Now comes the question. You have to extend this 3-dimensional cube perpendicular to the 4th dimension, which I cannot show because we are stuck in the 3rd dimension. You will get a Tesseract. So that is where you get the Tesseract. So in perpendicular direction, you have to extend the cube to the next dimension, you will get a Tesseract.
Okay, sir. Are the planets expanding and it will explode one day? Does that mean there is a probability for our parallel world to shrink? If so, then what about something comes from nothing?
The first question I answered. The second question, does that mean there is a probability for parallel world to shrink? So far, as I already said, our universe is accelerating. We don't know whether it will, the acceleration will reduce or it will go to a big string or a big crunch. So that's, we are not sure about, but so far it's accelerating. If you see the graphs, actually there are multiple possibilities. It can go like expansion and then acceleration, then deceleration, and to big crunch, and then again it starts again and again and again, like a big bounce, you can say. We don't have evidence for that. We only have evidence for accelerating universe. That's the first part. Then there you have asked, like, if so, then what about something comes from nothing? Yeah, definitely. It's happening throughout the entire time. That means the right in front of your nose, quantum fluctuations are happening, which means matter and antimatter, it's coming out from absolutely nothing and it's annihilating each other back to nothing. You can consider a very simple example like 1 plus minus 1, you get 0. Fine, we all believe that. But it's very difficult to believe that 0 is also equal to 1 plus minus 1, matter and antimatter. But that we won't believe. We are happy to believe 1 plus minus 1 equal to 0. So that is what happens. So absolutely nothing means absolutely nothing. There is no gravity, there is no mass, there is no any radiation. Even in such a space you take, which means absolute vacuum, even if you take like that, you will see matter and antimatter popping out just like popcorns that come out from the machine and annihilating each other and back to nothing. It is happening throughout each and every single point in the space. Yeah.
Okay, sir. Could you relate quantum entanglement and teleportation?
Teleportation, yes, which is one among the possible methods later in future. So quantum entanglement is one solution for it. Yes, we have teleported yttrium ions, and we have successfully done it from one particular island to another particular island. We have teleported these kind of ions, understand? The question is whether we can do that same for carbon atoms, hydrogen atoms, oxygen atoms, maybe molecules later, maybe objects later, maybe humans itself. Understand? So the entanglement is the key. The moment you make a change here, instantaneously a change is happening over there. Understand? So so that we can say that if entanglement is really happening, at one time you can actually teleport yourself into other part of the universe at one single instant itself. You don't need even light speed. Understand? We already know that light is the fastest within space, and even that is not required. You can actually overcome the speed of light and you can be there on the other part of the universe using quantum entanglement process. Maybe say after 500, 600 years, it might be possible to teleport the entire waste and garbage to say some Jupiter or to Sun. You can send it, understand, and make our planet clean. Yeah.
Okay, sir. Could deja vu be a memory of something that has happened to us in some parallel universe?
It's a very good question, but the sudden or the quick answer for that is deja vu. It's a feeling like, yeah, we have felt it somewhere before. And with respect to me, my personal view is that those are abstract memory recollections, which means you have, for example, imagine this torch. I have seen this. Fine, I have seen this. Now I'm going to somewhere else. I'm seeing this something very similar to torch. Maybe the torch itself of this type, or maybe something else. But I don't remember the actual one. Immediately the brain maps that you have seen something like this before. This is what actually happening according to the published journals and all. So the point is, what you actually feel is what you have already observed before only, but you are not actually recollecting where you exactly observed. Understand? So your brain is giving you some hints, some abstract memories. It's sending it to you and telling that, okay, you have seen this somewhere before, and I don't think it has anything to do with parallel universes. Yeah.
Okay, sir. What do you think of time inversion in parallel universe concepts used in Tenet's movie?
Time inversion is, according to physics, it's possible. What we are doing is reversing the entropy. Entropy reversal is possible, but nature don't prefer entropy reversal normally, but has happened before. For example, the very existence of ourselves, galaxies in the entire universe, if you see, it's actually kind of slight violation of entropy, you can say, because everything is expanding. Suddenly what happened to few things, suddenly it got, it's moving against the concept of entropy and getting accumulated, and all these stuffs are forming, the great things are forming. So they are having extremely low probability, but there is, that's the point. So in this vastness of universe, you still see these kind of low probability cases, and these galaxies, these planets, even the life itself is actually the reversal of entropy, you can say, because entropy always prefer to increase in the universe, and we ourselves are the clear-cut examples for the opposite of entropy. Now, according to time concept, yes, time inversion, mathematically it's possible. It's not getting violate any laws of motion or any thermodynamic principles are getting violated when you try to reverse entropy, because according to physics is also possible. The thing is probability. For example, you take a book, okay, and what you need to do is that, or you arrange 100 papers, okay, you just put page numbers in 1 to 100 according to the proper order, and you just throw it. Whether you get that papers in the same order back to your hand is the question. Probability says yes, but it is extremely unlikely. Understand? So that is the question. So if you can make it higher, make the probability, or if you can increase the probability of such a low probability case, then reversal of time with entropy is possible. Yes.
Okay, sir. So philosophy and science was once the same. Then it became two disciplines. Is there any possibility that it can be combined again?
That's a very good question. Philosophy was actually the, it was a building block. That is the way we actually start thinking. Understand? So philosophy had a key role in the development of science, but science has its own ways. That's the difference. Understand? Science won't wait for any, literature, philosophy, or history, or maybe even superpositions. Science has its own way. The measurements that you're taking, understand whether it is happening again and again. Understand repeatability. The one among the important property of science is repeatability. For example, if you are having a medicine, okay, for fever, just imagine, and your fever is going, whether that is happening to you in all the places, or whether that is happening to many people at different places, then it is something scientific, the medicine you had. Understand? So that kind of observational results and experimental results make science. Yeah, but it's not 100% what you can say. It might not work, but still, if it works 90%, it is scientific. Understand? So philosophy, yeah, that's the way to start thinking. Keep thinking, keep dreaming, and these things can happen. The God can exist. All those things you can bring together, but you need evidence. All those things what I said today need evidence. Other than that, it's just piece of fictional stuffs. Yeah.
Okay, sir. So negative mass and negative energy, do they exist? How can it help? Can this help in time travel?
The concept of negative mass and negative energy. Negative mass and negative energy, how we can say is that, imagine you are going to a beach, okay, and you take a shovel and you are starting digging, okay, and you are making a pile of sand at one place. So that is one way you can say the positive energy or positive mass, where that hole that you created is the negative mass or the negative energy. That is one way of thinking the negative mass and negative energy. Okay. Now, for time traveling things, you have asked for time traveling in that. Yeah, yes. Right, fine. So for time traveling purpose, you need the help of negative mass and negative energy. How this happens is through quantum fluctuations. How that happens is that during quantum fluctuations, there is a possible pattern for forming the negative mass and negative energy. Extremely unlikely. We call it the Casimir effect. You can refer the Casimir effect. And this Casimir effect, which is not stable at all, which is really unstable. So that situation, that particular arrangement of particles that came out of fluctuation can create a negative mass and negative energy and can help you for time traveling. How? For example, take a black hole. At the center, I already told that it is extreme finite, extremely high density, and in order for a space to go through that, negative energy should be there. Understand? Otherwise, you cannot actually go through or pass to the other side. So negative energy is what actually keeping the what I can say, the holes open. Understand? Negative energy. Why? Because according to gravitation, everything likes to be go into it and get attracted, but negative energy pulls it back. Understand? So there should be negative energy or negative matter for us to go to other universes or time traveling. And I think that's the only key. You need to find some way to arrange these quantum fluctuations into a particular pattern to get this negative matter and negative energy. Yeah.
Okay, sir. Is going to the future or to the past easy?
I believe it's going to future itself is the most easiest way. You just need to do is that you take a rocket, you go out to the space, you just make a round trip with black hole. That's it. You are back to future. So going to past is not easy. Why? Because going to future, what you need to only do is that you need to go out and come back. That's only you need to do. Gravity will do the rest. But going to past, that's not the key. That's not the way how we have to understand. One thing we can say that is, instead of going to past, what you see is past itself. That way you can say that you are already seeing the past. For example, you all are watching me, right? Say 61 people are there right now, and you all are watching me. What you actually seeing is my past, because milliseconds before I have already said something and it's reaching right now only. Understand? You look out and you go out and look at the sun. You are seeing 8.5 minutes, the sun of 8.5 minutes before. You are seeing the past. You go out and look at the moon. What you are seeing is the moon of 1.5 seconds before. Basically, once again, you are seeing the past of the moon. All the stars on the night sky, the entire stars in the night sky, what you are seeing is the past of them millions of years before. Understand? So that way we can say that going to past, but other than that, physically moving to past is very difficult.
Okay, sir. The butterfly effect is affecting the parallel universe.
I think that's a statement. Fine. Okay. Butterfly effect or chaos effect. Yeah, that definitely affect. For example, all these things what I said right now, at least one among you are actually taking into your heart, and imagine that that one person is taking science for their higher level education and going like that. That might make a change in the world somewhere later. Understand? So we can say butterfly effect. Mathematically we can prove that, and also we can say philosophically also we can say that it happens, and that's actually everything works. Yes, any tiny thing that you do is affecting the future. Yes.
Okay, sir. So photon is its own antiparticle. Do they annihilate each other?
Photon, the problem is the standard model of physics. Understand? The standard model of physics, we know that quarks are the leptons, and other energy carriers like photon, gluon, and bosons, and all those things. We say if you take the energy carriers, how you should understand the photon is like it is like bucket and water. Understand? For example, imagine a large bucket you have, okay, and then a medium bucket, and then a smaller bucket, and very, very tiny bucket. Okay, these buckets you can name it as, the first one you can call it gluon, the second one you can call it as photon, the third one you can call it boson, and the fourth one you can call it as graviton, not yet found out. Fine. Now the water inside that, the first bucket, okay, inside that gluon bucket, if you look into that, you can see water. Okay, fine. That water, you can call it as strong nuclear force. Photon, you can call it as electromagnetic force, the water inside it, because photon carries the energy of electromagnetic force. Third one, boson, weak nuclear. Fourth one, gravitational. So the point is, photon itself has got no mass. Understand? Photon itself has got no mass. So matter and antimatter, when we say, it's not a, there we can say the annihilation, but when it goes to radiation, we can't say that. So basically, an electromagnetic wave, photon has got basically no annihilation, and you can also say that it interacts. Actually, it gets superimposed. One way you can say the annihilation is that a crust and trough meet together and you get nothing. Yeah.
Okay, sir. Can you explain how Einstein's model of gravitation causing high tide and low tide?
General relativity is what you are referring to. Like, how you should understand is that, imagine a rubber sheet. Okay, you keep a heavy ball at the center, you take some marbles, you throw into that. These marbles actually will roll. Okay, it will roll through that rubber sheet and it will eventually fall into that heavy ball. Fine, that much you understood. This is happening not because of the gravitational pull of that heavy ball. It's because of the that entire rubber sheet got curved or warped. Understand? It got warped, and because of that heavy mass that we have kept at the center. Sun, that heavy mass. Marbles are planets. You throw these marbles, what happens is that these marbles will roll around this heavy ball the same way the planets are revolving around the sun. They are, when we say that they are gravitationally connected, it's not because of a force. Understand that. Gravitational force is just a myth. What's happening is that this warps in space. So here, the tidal effects, understand? We have the Earth here, Moon is nearby, and Sun is there. Sun and Moon both contribute to tidal effect. Moon is contributing more tidal effects. So the same thing is happening. When Earth is at the center, let's take Earth as the center. The space which contains the Earth is getting warped where Moon is there. So in that spatial curvature, Moon is there, which is revolving around the Earth. And now what's happening is that this is exactly how you should understand the gravitation. Understand? So this pulling effects, because of this warping of space, make the what we can say the shape of the Earth into a geoid shape, and it's getting pulled because of there. On the other side, Moon is also creating a small warp in space or curvature in space to which Earth is trying to fall. Understand? But there is no force. Understand? I hope it's clear. So tides are created because of these warps in space and not because of pull. Yeah.
Okay, sir. So we have a particular imagination of aliens. Are they the future humans? Is that a glimpse of our future? Something like what we see in the Interstellar about the future me trying to tell the present me something.
Yes. If you are asking about the okay, one second. Particular imagination of aliens. Fine. The aliens, what you are trying to imagine, maybe that green colored thing with large heads, brainy heads, you can say, there are without eyelids and all the black color stuff. That is what you can see in movies. I don't think you will ever find an alien like that. But when we say aliens, even a microbe, understand, which is not in our Earth, is basically an alien. Understand? Imagine the natural satellite of Saturn, or you take Titan, or any satellites you take, natural satellites. Imagine there is life, maybe in a bacterial life or microbe life or something like that, but not complex life. They are aliens, and if at any time we are going to there, we are aliens for them. Understood? So the concept of aliens, when we understand, you should understand that if you are actually trying to connect with higher intelligent aliens, it's extremely unlikely because we don't have any evidence even till now. Understand? We are sending radiations daily from SETI or Australia. We are sending a lot of radiations, no reply at all, and we hopefully one day we might get some meaningful reply from any corner of the universe.
Okay, sir. If the whole multiverse is existing by possibilities and probabilities, then is the statement God made everything valid? Do you think there is God?
My direct answer for that is no. The thing is, we don't have evidence. If there is evidence, fine, we are ready, or I am ready to believe. But till now, we don't have any slight evidence for it. All these things, what you might be saying, is experience. Experience is not the way science works. Science needs proper evidence. Listen, it needs repeatability. That's as I already told. If you're seeing something very unlikely, understand, something you can say miracle, the word, if you are using that miracle, it should be repeated, understand, or it should be able to explain, understand. All the miracles till now what has happened can be explained scientifically, so it cannot be treated into the category of, what you can say, that's sky daddy or something like that has created all these things. But according to physics, it all evolved, and it came from absolutely nothing. You don't need actually a creator to explain all these things and how these things are working right in front of your eyes. Yeah.
Okay, sir. Can you explain butterfly effect?
The slightest disturbance that cause a huge commotion, I can say like that, or a huge chaos, that is basically butterfly effect. So even the tiny vibration of atoms can later on result into a huge issue or huge, or you can say in the terms of butterfly, the butterfly when it flies, okay, its wings are moving up and down. That is actually enough to create a, what you can say, tornado at other point of the earth. So even though that doesn't make sense, it's just, that word is given to make you understand that how difficult that's, or how, what I can say, complex this stuff is, understand. So slight tiny atom, when it moves or vibrates, it can reflect at some other part of the world in some other way. Yes, maybe the stock itself. Yeah.
Okay, sir. We know that our planet will also explode a day. In that case, will our planet world undergo the same destruction? Is there any possibility for our world and parallel world vanish forever at the same time? If so, what else will exist? Then, will there be any evolution of the same since something comes from nothing?
uh, it depends upon how physics work in other parallel universes. According to our knowledge, according to the inflation theory, by Alan Guth, the thing, what he says is that the universe that we are living here, the physics how it is working here, may not be the way how it works in other universes. So even though you can generalize that all the universes might have come from Big Bang, which is how the max is showing, it's not necessary that all the physics that work here is working there itself. Maybe in some other universes it might be expanding and going back to the big crunch and it's getting vanished. But right now our universe is expanding. Maybe some other universe at some other distinct point, we can say that it gets collides with our universe, and the gravitational ripples we will detect at some point of time, and we'll be able to say, yeah, that is a clear-cut evidence for multiverse. Understand? So we are patiently and eagerly waiting for these kind of ripples. At one point, maybe right at this instant, you can see the paper tomorrow and you can check the headlines that multiverse theory is proved by detecting cosmic ripples. Understand? So that's what the parallel universe, not necessary to obey our physics. Yeah.
Okay, sir. Will we ever be able to beat time or prove the theory of relativity?
Beating time. Actually, I don't understand what meant by beat. I understood the word meaning. The problem is there are some questions you can frame it with a question mark, but you can't actually give an answer to it. For example, why electron is blue in color? It's a question, but how will you explain that answer? So that is the problem of beating time. Is according to relativity, present, past, future all exist at the same moment. That's the problem. So there is no point in beating at all, because you are already existing at that particular moment. You can switch to future, you can switch to past, because they all exist at the right very moment. Understand? So beating time, that part, uh, I have explained, then prove the theory of relativity. Will we ever be able to beat the time or prove the theory of relativity? It's proven. It's already proven. Special relativity, if you are mentioning 1905, it's proved, and general relativity 1915, it's also proved. But there are some places, and that's why he didn't get the Nobel Prize for relativity. There are some places where this relativity will break. For example, at the center of the black hole, you can't apply the relativity concepts. Yeah.
Okay, sir. Is there a possibility that we are living in a mirror dimension? What is time? Is time the only key that we have which can unlock every single secret or which can redefine your knowledge about everything?
Is there any possibility of us living in a mirror dimension? Maybe. That's what we can say. We are actually locked in 3 dimension. We are not able to go to higher dimension. One way you can think is like this. Imagine a multinational company. You are working in a ground floor and you have an access card only to the ground floor. Just imagine. You can't go to any other floors. So what you can do is that you can wait at the door of the first floor or second floor and wait for someone to open the door so that you can sneak in. Understand? This is how we can only go to higher dimensions. What I meant by opening the door is some kind of wormholes should be there. It should be um, placed by some higher intelligence so that it's an open portal. You can go into it or you can come out of it, but once you go into it, we don't have any guarantee that it might get collapsed suddenly. So you have to wait for that wormhole. Is it actually getting open for a long period of time? Otherwise you will be stuck into that higher dimension. Understand? That is the answer for that first part. Second part, what is time? No idea. I can't explain what time is, because that is one thing that no one can actually give a proper definition. Listen, we feel time. That's all what we can say about time. Is time is the only key? May not be, because we need to know about higher dimension and how it works. Time is considered as one among the dimension. So we need to know the other dimensions too to reveal the actual reality. Maybe string theory can do it. Yeah.
What are your thoughts on humans being a multi-planetary species? Also, there are people who think we should use the resources that we are spending on going to Mars on saving the Earth, and also those who are saying we should do both. Also, scientists are saying we have a maximum a decade or two to turn the climate change problem around, and then it will be irreversible.
Yeah, this is a question that most of the people ask to scientist community, that why you need to go to Mars where so many issues we are already dealing with here. The answer for that is you will be able to make a colony in planet Mars only if you are, if you have solved most of the issues on planet Earth itself. But you have to do it together. Understand? Imagine that you are planning to do all these things only after, by seeing the Earth as a wonderful world, like in your imagination. You will never go to planet Mars, you will never go to Moon. The human civilization should go on. That is the key thing. Even if the Earth gets destroyed, the human civilization should go on. For that particular reason, we have to go to Moon first, Mars second, natural satellites of Saturn, Jupiter. Then we have to go to Mercury. Venus is a possible option too. And then we have to step into the next galaxy itself. And then we have to keep moving to different galaxies, universes, multi-universes, megaverse, and it goes on. So that we have to do. That is the way we should live. Why? Because by planning to go to space itself is that is a key reason why we are using the laptop now. That is the key reason why you're using the toothpaste now. I have said this in a previous talk. So the toothpaste or all these things come from the research based on space inventions. Understand? So all these things we are using right now without knowing that these were the things actually used in space first. Understand? By astronauts, and for their purpose it got invented, and right now we are using it in our daily life. Yeah.
Okay, sir. Sir, could there be no parallel worlds and it's need to be replaced by some other discoveries? Is there any evidence of existence of parallel universe?
We don't have any trace of the evidence for parallel universe, and we are actually looking, or we are actually in search for these kind of things, whether it exists or not in for example, what we can say, one method is LIGO. Understand, you the gravitational waves, if it is coming, or maybe LHC, Large Hadron Collider, we might get some supersymmetric particles if you are getting. But I do say that it's very unlikely to get supersymmetric particles from LIGO, from LHC, because it's not, the energy is not enough, understand, to create these kind of supersymmetric particles. And if you, just imagine you find one fine morning you are getting, like we found Higgs boson, imagine you are getting supersymmetric particles, that is enough that you can prove that higher dimensions exist. If higher dimensions exist, string theory exists. If string theory exists, there is a high chance for existence of multiverses, which is basically you can call parallel universes. Yeah. So we are waiting for it. Yeah.
Is it true that alien species really exist as seen in some comic books?
As seen in comics books, the answer is we don't know. Why? Because we don't have, again, no evidence for it. We are in search, but how we are searching is the most funny thing. We are sending radiations. We are sending light waves, understand, through radio waves we are sending. The problem is that it can only travel up to 200 light years, and after that it will get, it will get decayed, it will get absorbed by the space itself, and it will turn into noise. It will get redshifted, understand. So the problem is, even if there is a higher intelligence, some say 200, 300 million light years away, or even on the other end of the Milky Way galaxy, they will never be able to understand or decode what we have sent. Understand? That's the problem, because the signals that we have sent already turned into noise. So we don't actually see any artifacts in space right now. For example, imagine, have we ever seen something moving from one point to another point, like a glowing stuff, which is working as a mechanical stuff? No, we haven't seen. So we are actually paying a close attention to space. We are observing each and nook and every corner of the space, but we haven't seen anything really like that.
Why does forces exist?
It's again an unanswered question, because the problem is something is existing right there. We have to know about the 10 raised to minus 43 seconds before the moment Big Bang has started. We have no clear idea why they exist on the first place. All the four fundamental forces that we do study now has actually started from one single point. All these forces were one single force before, and we have combined few of them. And in the initial stage of the universe, we don't have any clear-cut idea, because cosmic microwave background is actually stopping our view beyond that particular point, which has happened 38,000 years after the Big Bang. So the problem is, you are actually getting covered by a shield. When you use the telescope and actually look into the outer space, as you go further and further, what you're seeing is actually a plasma shield you are seeing, which is CMB waves, and you can't see actually what's happening beyond that. So we won't be ever able to maybe prove that why forces exist on the first place. Yeah.
Okay, sir. I think the next one is the last question. Does electromagnetic spectrum pose to be a limitation? Can there be something beyond it?
Maybe it depends upon, and we have got some evidences, some what we can say traces of the existence of the fifth force. And if that is true, then we might find another particle into the standard model. And in that case, there might be a extension of electromagnetic radiation, possibly. And till now, we don't have any idea about it. Maybe, what we can say, for example, we right now till the waves start from radio waves, and it ends at the gamma wave spectrum. And beyond that, Is there electromagnetic waves there? We haven't seen any evidence. Maybe a dark energy might be the solution for that. Understand? Dark energy might be consisting of these kind of radiations which we don't know. And once in a blue moon, this dark energy, the dark matter is actually interacting with matter once in a blue moon, and it's giving out radiations. So maybe this kind of radiations might be, or the dark matter or dark energy might be the solution for the fifth force or the extension of EM waves. Yeah.
Okay, sir. I think we have one more question. So, do you think science can explain morals?
Do you think science can explain? Yes, we do have all these things, in our brain itself, and that is how you can evolve itself. You don't need science to explain morality. Understand? We are evolved creatures, and we are still evolving. Understand? And all these things are right there as inherent properties, and it all depends on whom you are interacting, where you are living, and it all depends on what you can say, the people whom you are dealing with. Understand? Morality comes from there, and it's not something to be injected by from an external stuff. What you see and what you learn is how you behave. Actually, you don't need science for that, but science actually can trigger it. Understand? Can actually help it to make it more beautiful and wonderful world.
Okay, sir. I think we are done with the questions. Thank you so much, sir, and thank you so much to all the participants who have shown this much enthusiasm. Now I would like to invite Samyukta for the official vote of thanks.
Good evening, everyone. Hope you're all safe and doing well. First of all, I would like to thank all the participants for attending this session, even amidst all these adverse conditions. And without you all, this couldn't have been such a great success. And I would like to thank our speaker, Mr. Paulose Thomas, sir, for preparing such an informative and engaging session for us. And from the interactive session and all, we know you all enjoyed the session a lot. And let me take this opportunity to extend my sincere gratitude towards our faculty coordinator, Ravi Roy, sir, who couldn't attend the meet, unfortunately, because of some reasons, because of these climatic conditions and all. And I'd like to thank IST, TKMCE for all their support, and we extend all the support to their upcoming technical fest, that is Athena. And last but not the least, I'd like to thank my entire team of Astron TKMCE for being with us and for organizing and conducting this event. Thank you so much, and stay safe.